Okay, so this is section 8.1. We're going to be talking about linear systems. So we're going to move from just one equation to linear systems, a system of equations. Okay, so just to give you an example of, you've already seen linear systems. So that first week of class when we were looking at some of the preliminary information, we talked about predator-prey systems. And so basically, with a predator-prey system, you have two different species. So here we're calling them X and Y. And predator-prey, one benefits from the other, and the other one is harmed by one of the species. And so with the predator-prey, you're looking for, so the XY term represents interaction between the two species X and Y. So here, the change in X is going to be positively affected by this interaction, and the change in Y is also going to be positively affected by this interaction. So this is not a predator-prey system, but instead, since they're both positively interacting with each other, then they're called a cooperative system. Okay, so now in the second one here, you have two minuses in front of this interaction. So the change in X is decreased by this interaction, as well as the change in Y is decreased by this interaction. So then this is what's called a competitive system. So the more that you have of one of the species, then the more that it's going to affect your own species. Now, this last one is a predator-prey system, so this is one that you actually saw in one of your homework assignments. And so here you have a negative, so X is being negatively impacted by this interaction, whereas Y is being positively impacted by this interaction. So it means X is the prey and Y is the predator. So this was an example. So each one of these is a linear system. In each one of these cases, it's a linear system of two equations. Okay, so another linear system is this equation here. So the way that you actually get this equation is you actually have, instead of, we've looked at mixing tanks, and so that was a big thing that we had before the midterm. So here we have two tanks, and so we have pure water coming into tank A, but we also have a mixture coming into tank A as well. So then the mixture is leaving tank A and going into tank B, and then in tank B, a mixture is leaving tank B. So if you actually look at the input, so here into tank A, you're going to have an input from pure water, and you're also going to have an input from tank B, and you're going to have an output here. And so you can actually go through, do the exact same thing we did with just one tank, and actually derive a system of equations for both tank A and tank B, because what leaves tank B is going into tank A, what leaves tank A is going into tank B. Okay, so you can derive this system of equations that represent, and this should be an XB right here, but this represents a model here, a linear system. Okay, so a first order system, a system of n first order equations is called a first order system. So basically you have n equations that are all of the first order. So remember, first order means that the highest derivative that you see is the first derivative. So a first order system written in normal form basically looks like these equations. So here you have dx1, the change in x1 is related to some constant times x1, so this doesn't actually have to be constant, this can be a variable. Then you have, it's related to x2 and xn plus some forcing function. And so here you have n different variables in here, and you have the change in each one of those variables and how it's affected by each of the variables in the system. So in general, these can be zero, they can be polynomials, they can be some function of t, they can be constants. And then here you have your forcing function, so if these are not zero, then you have a non-homogeneous system. Just like if we were looking at one equation and we had f was not equal to 0, then we would have non-homogeneous. So a system of differential equations is typically called a linear system, just like in linear algebra you had linear system of equations. And just what I said previously was that if all the fi are equal to 0, so in every single equation here, if each one of these is equal to 0, then it's called a homogeneous system. If even one of them is non-zero, then it's called non-homogeneous system. Okay, so what you're going to end up seeing and what we're going to end up working with are the matrix form of the equation. So just skipping back up here to this equation, you can notice that on the left hand side you have the derivative of a vector x1, x2, all the way to xn. And notice these are written a lot like a matrix is. So basically you have something times x1 plus something times x2 all the way to something times xn. So we put these a's into a matrix, we put the x's into a vector, and we put the f's into a vector. So here's our x's, here's all of our coefficients, and here's our f as a vector. So basically the derivative of this, so here x prime, the derivative of this one, is equal to this matrix times the vector x plus your forcing function. So written in matrix form, so if we have this linear system and we want to write it in matrix form, so we know that our capital X, our vector, will have the variables x, y, and z. And here we have a 1 in front of the x, a -2 and a 1, a 2, 1, -1, and a 1, 1, 1. So we're going to let x be x, y, z. The coefficients in front of your x, y, z here become your matrix A. So again, this is a 1 that goes here in the first column. Make sure these are in the same order as what you put x, y, and z here. If they are written in the same order, then you can just pick off the coefficients. So what's in front of the x, it's a 1. What's in front of the y, it's a -1. What's in front of the z, it's a 1. So because then you have this row times the x, y, z should give you this. So you have 1 times x minus 1 times y plus 1 times z. And then you put all of the first forcing function terms into this last one. So this is your A and this is your F. Okay, so now going backwards, we can write this as a system. So if we have the derivative of x, y, z, on the left hand side we're going to have dx, dy, dz, dx, dt, dy, dt, dz, dt. Here, to get our first row, our first equation, we're going to take this row times this column and add them. So we're going to have 1 times x minus 1 times y plus 2 times z plus 1 e to the negative t minus 3t. So that's what's going to be in our first equation. So again, 1x minus 1y plus 2z plus 1 e to the negative t minus 3t, which is what we have in this first one. So then the second term here, dy dt, we're going to now read across this second row. So we're going to have 3 times x minus 4 times y plus 1 times z. So here, that's that term. Plus 2 e to the negative t, and then this would be plus t. And then lastly, we have dz dt is equal to last row. So we're going to have -2 times x plus 5 times y plus 6 times z. Reading off the last entry here, we have plus 2 e to the negative t minus 1t. So we get this system. Okay, so what does it mean to be a solution vector? Just like in the one-dimensional case, one equation case, basically it's a solution vector if it satisfies this equation. So to verify that it's a solution vector, basically what you want to do is you want to plug it in. So here, this is saying that my solution is 5 cosine t times e to the t, and then 3 cosine t minus sine t, all of that times e to the t. So to see whether or not it's a solution, we want to see whether or not it satisfies this. Okay, so let's write it in matrix form. This is the easiest way to check. So if we write our system in matrix form, so going back up, this system, I just put it right back up on top here. So writing in at matrix form, the left-hand side, we have the derivative with respect to t of our vector xy. Here we have x and y in order. So this is -2, 5, -2, 4, just picking off the coefficients. Okay, so now what we want to do is we want to plug in what we're trying to see whether or not it's a solution vector. We want to plug it into the left, and we want to plug it into the right. So here, this is x. So basically 5 cosine t e to the t. if I take the derivative of this, so I want to look and see what the derivative of the left-hand side is. If I take the derivative of this thing, I have to use the product rule. So I have e to the t times the derivative of this, so I get minus 5 sine t times e to the t, plus I have 5 cosine t times the derivative of e to the t, so I get 5 cosine t e to the t. So again, the derivative of the first, I'm going to have minus 3 sine t minus cosine t times the derivative of the second, so that's just e to the t. And then the second times the derivative of the first times the derivative of the second, so I have 3 cosine t minus sine t times the derivative of e to the t, I get e to the t. So this is my x prime, this is my left hand side here. So now I need to see what this right hand side looks like. So here we need this to be true, where x is equal to this. So let's look at this right hand side. We already know that x prime is equal to this. This was what was on the previous slide. All I'm doing here is just rewriting it as one term. So this is minus 5 sine t e to the t plus 5 cosine t e to the t, just writing it together as a vector, because we're going to want to equate what the vector is when we multiply the matrix times this vector. So we're just writing it as one term. So when I combine this one, I have minus 3 sine t e to the t and minus sine t e to the t. That gives me minus 4. Here I have minus cosine t and a plus 3 cosine t, so that gives me a plus 2 cosine t. Okay, so now we need to find the right hand side. So we look here at the right hand side. So basically, if I take this row times this column, I'm going to have minus 2 times the 5 cosine t, so that gives me minus 10 cosine t. Then I'm going to have the plus 5 times this part, so I'm going to have a 15 cosine t, and then when I multiply the 5 times this one, I'm going to have minus 5 sine t. The e to the t can just stay on the outside. Second row times this column, I have minus 2 times the 5 cosine t, so I get minus 10 cosine t. When I do 4 times this one, I have, that's 12 cosine t minus 4 sine t, so 12 cosine t minus 4 sine t. So just join like terms. This gives me a 5 cosine t minus 5 sine t. And this gives me a 2 cosine t minus 4 sine t. So if I look at these, they're just written in backwards, but they're the exact same thing. So my left hand side is equal to my right hand side, so it's a solution. So we verified it. Okay, so then there's this theorem that says basically the solutions exist if the entries of a of t and f of t are continuous on some common interval that contains some initial value, then there is a unique solution to the initial value problem. Okay, so let's look at this system. Okay, so if we look at this system, what it means to have a unique solution is that my a and my f have to be continuous on some intervals. So here my a is constant. This function e to the negative t, this is continuous, so the sum of these is continuous, so my f is continuous. So there's a unique solution if I'm given an initial value. Okay, so in the one equation case, we had this superposition principle, which basically said if we had one solution, or we had two solutions, or we had n solutions, we could add them together, and that would also be a solution. This is exactly what this says. So if we have vector solutions, solution vectors here, then we can add them together to get a solution. So remember how we found our solutions previously for the one equation case. So if we had a second order equation, then we needed two linearly independent solutions. So that's the exact same way we have here. So we need linearly independent solutions on our interval, and in this case we need as many linearly independent solutions as variables. So if we have n variables, we need n linearly independent solutions. And then once we have linearly independent solutions, then we can add them together to form, and they form the fundamental solution set, and we can add them together to get a general solution. So what's it mean to be linearly independent? It's the exact same thing as before. So it's dependent if there is some non-zero constants such that when I add these together I can get 0. If there's not a non-zero constant, if all these constants have to be 0, then they're linearly independent. So this is not the way that we figured out whether or not something was linearly dependent or independent last time. We actually used the Wronskian, which we do exactly that here. So what we do for the Wronskian, so the Wronskian when we were talking about our single solutions, we put previously we had the function, we had the derivative of the function, etc., etc. This time what we actually have is we have the Wronskian of vectors. So this x1 is a vector, that goes as my first column. x2 is a vector, it's my second column. All the way up to xn is a vector, that's my third column. So these are our vectors. You put the vectors into a matrix and you take the determinant of it. If it's not equal to 0 for every t in the interval, then it's linearly independent. So if we have n linearly independent solution vectors to our homogeneous system, then it's said to form a fundamental set of solutions, just like what we had in the one-dimensional case. So all of this should seem really similar to what we had in the one equation case. Okay, so then if we have a fundamental set of solutions that are linearly independent, then basically we can sum them all together to get our general solution. Okay, so let's look at this. Let's look at figuring out whether or not these are independent. So the first thing that we have to do is figure out whether or not they're linearly independent or not is we have to find the Wronskian. So here, this x1 vector is just 1 e to the negative 2t. That's this right here. 1 e to the negative 2t. That's this right here. So this is our x1. This is our x2. So it's 1 e to the negative 6t minus 1 e to the negative 6t. This is our x1. This is our x2. And then from there you find the determinant just like we always do. So you're going to multiply these diagonal elements. So I'm going to have minus e to the negative 8t. And then I'm going to subtract off when I multiply the off diagonal elements. So here I have these two multiplying together minus these two multiplying together, just like before. So combine them, I get minus e to the minus 8t minus e to the minus 8t. This is just minus 2e to the minus 18. This is not equal to 0 for all t on my interval that I'm interested. So if it's not equal to 0, then it is linearly independent. So it forms a fundamental set. Okay, so now let's look at this one. So this x is just a vector. If I combine these, I have 1 plus t minus 2 plus 2t, 4 plus 2t. It's just a vector. Same as x3, 3 plus 2t minus 6 plus 4t, 12 plus 4t. So if I'm looking at this, I do it the exact same way. If I want to figure out whether or not they're linearly independent, I write them as columns. So here's my x1, here's my x2, and here's my x3. So I'm going to do the exact same thing as I did before. So I'm going to take my 1 plus t. Remember, so the determinant, I'm getting rid of my first column, rid of my first row, and I look at the determinant of this little part down here. And then I'm going across my top one. So I'm going to expand across my top one. So remember, I have plus. This has a minus in front of it. That's why I have a minus 1 here. So I'm thinking about getting rid of this first row and my middle column. So what is in my matrix is these two and these two. And then I have plus 3 times 2t times this determinant here. So the determinant is if I get rid of the first row and the last column, I have this part in here. So again, this is what I have. I need to finish figuring it out. So here, this first part, I have 1 plus t. I'm going to multiply the negative 2 times this term minus 4 times this term. Same thing here. I'm going to have a minus on the outside. I'm going to have the negative 2 plus 2t times the 12 plus 4t minus when I multiply these two together. And then my last one, the 3 plus 2t stays on the outside. What I get here is the 4 times this negative 2 plus 2t minus this negative 2, so that's where this plus 2 comes from, times this 4 plus 2t. So then simplify everything. So all of this in here simplifies to negative 24t. Then inside this one, I full out both of these. And so here, notice that I full out both of these. So here I'm going to have a negative 24 plus a 24. Here I have a 16 minus a 4. And then here I have an 8 minus 8t squared minus 8t squared. So I can simplify all of this. So here I have negative 48t squared. No, sorry. Here I have negative 24t squared plus 24t squared. Those cancel out. Those give me 0. Here I have a negative 24t and a negative 12t. That gives me negative 36t. I add that to the 36t, and this gives me 0 for all t. So it's linearly dependent and does not form a fundamental set. Okay, so now if we want to prove that we want to prove that that this forms a general solution to our linear system, then there's two things that we have to do. We first have to show that our x1 here, our x2, and our x3 are solutions to our equation, and then I have to show that they're linearly independent. Okay, so showing that they're solutions. So here's our x1. If I look at x1, I take the derivative of this. So the derivative of e to the negative t is negative e to the negative t. So I get negative 6e to the negative t. When I multiply this by the negative, I get 1e to the negative t. Multiply this by the negative, I get 5e to the negative t. So now I need to do my right-hand side. So here's my matrix times my x1. So plugging in this here, then going my row times my column and adding them all together. So I'm going to have 0 times this plus 6 times this. So that gives me minus 6e to the negative t plus 0 times this one. So that's where I get this minus 6e to the negative t. My second row times my column. Here I'm going to have a 6e to the negative t, 0 times this one, minus 5. So that gives me the 1. The last row times this column, I have the 6 minus 1 plus 0. So that gives me the 5e to the negative t. So notice this thing, my x prime, is the exact same thing as my ax. So, since they're the exact same thing, the next one is a solution. I can similarly show that x2 and x3 are solutions by going through the exact same process. Okay, so now let's show that they're linearly independent. I put them as my columns in my Wronskian. And then again, I'm going to go across this top one. So I'm going to have plus 6e to the negative t times this part. I'm going to have the minus a negative 3, so this is where that's plus, times my these two and these two, and then plus 2e to the 3t times this part. So multiplying it all out, I can multiply it all out, combine like terms. I get that this is actually just 12 plus 8, or 20. It's not equal to 0, which means that they're linearly independent. Since they're linearly independent and they're all solutions, then C1x1 plus C2x2 plus C3x3 form a general solution. Okay, so for non-homogeneous systems, we let xp be a solution to the non-homogeneous part, and we let our xc be the solution to our homogeneous part. So just like before, our general solution to a non-homogeneous equation is our solution to our homogeneous part plus our particular solution. So if I want to verify that this thing is a particular solution to this system, then we do just like before. To verify it's a solution, I'm going to plug this in everywhere I see x. So here I'm going to look at this, I'm going to take the derivative of it, that's what's going to go on the left hand side. I'm going to look at this, I'm going to multiply it by this matrix, and then I'm going to add this part to it. So if I look at this, I multiply, I take the derivative of it, so the derivative of constants are just 0, so this goes away. Here I have negative 2 times t, the derivative of that is just negative 2, derivative of 6t is just 6. So I look at the right hand side, so I want to take my matrix times my xp, and I want to add to it this. So if I look at this thing, so here I have negative 2t minus 4/7. So when I do this, I can do this matrix times here. So here this is be negative 12 plus 6. So it gives me a minus 6t. Here I have minus 8 plus 18. That gives me a plus 10t. When I take the matrix times this one, so I'm distributing it through. So I have the 6 times the negative 4 sevenths. So I have negative 24 sevenths plus 10 sevenths. So negative 24 sevenths plus 10 sevenths gives me negative 14 sevenths, or negative 2. Similarly, here I'm going to have minus 16 sevenths plus 30 sevenths. And so I'm going to be able to simplify that to positive 2. And then I have this right hand side adding up. So now if I look and I add this together, so here I have a negative 6t minus 2 plus 6t. The 6t's cancel and I'm just left with negative 2. The bottom one I have 10t plus 2 minus 10t plus 4. The 10t and negative 10t cancel, and so I add 2 plus 4 gives me 6. I get the exact same thing from my right hand side as I got on my left hand side, so it's a solution. So this example says use the information from the previous example along with the fact that these two are solutions to the homogeneous system and find a general solution to the non-homogeneous system. So if we know these are solutions to the homogeneous system, and on the previous one we showed that this was a solution to the non-homogeneous system, then to find our solutions we're going to take a constant times this plus a constant times this plus our xp. So here, constant times our x1 plus constant times our x2. Our xp is this. Join them together. So this is our complementary part. This is our particular part. And that's our general solution. And that is all of 8.1.